Hello and welcome to New Scientist Weekly, your curated selection of the week's science stories. I'm Christy Taylor, currently in Portland, Oregon.
And I'm Sophie Bushwick in New York. This week on the podcast, how climate change may affect the fate of shipping in the Panama Canal. New research on the relationship between microdosing LSD and complexity in your brain. And Iceland's dramatic recent volcanic eruptions, they're even more dramatic than we thought.
Plus news from Bennu, the asteroid that might actually have come from a world with an ocean. But first, this week we had two exciting bits of news on the fusion energy front. One reactor in the UK claims to have set a new record, and we'll get to that in a moment. But also there's Lawrence Livermore National Laboratory, where a reaction has reached the point of breaking even in terms of energy out versus the energy it takes to do the reaction in the first place. Matt Sparks is here. Matt, I definitely remember a similar claim about a year ago from the same lab. Does this actually get us any closer to a new source of clean, reliable energy?
Yeah, you're right. This is a confirmation of a previous result, but a bit more as a bonus as well. So in 2022, there were rumours that later got backed up by an official announcement that the lab's inertial confinement fusion experiment had broken even. Basically, that it had created the same or more power than was put in to sustain it. That's a really crucial point because really there's no reason to build a power plant that consumes more power than it generates. It's not a good business model. So what we've seen this week is 5 peer-reviewed papers confirming that result. And they also revealed that they've bettered it since. So the 2022 experiment put out 1.5 times the power consumed. And we now know that another run in September last year pushed this to 1.9.
Okay, that's quite a jump. But presumably that's not exactly the sort of jump that means that we can now build, practical fusion reactors and push clean, plentiful energy around the planet, thus solving climate change in one fell swoop and then holding hands and singing about it, right?
No, not by a long way. For one thing, the ratio of energy in to energy out is based on the output of the lasers that kickstart the reaction. But they're really inefficient. So the true amount of energy you put in is vastly higher. Then you've got the problem that ICF reactors, they fire once for a really brief moment of time, and then they take at least a day to reset. So a practical reactor would need to fire many, many times a second in order to be useful. Then there's a handful more of those sorts of enormous problems that also need to be overcome, including reliably making the fuel pellets, extracting the power in a useful way, and all of that sort of thing. But it's a really good result, and it's one which pushes at the boundary of our understanding of nuclear fusion.
People often joke that fusion power is 20 years away, and it always will be. So does this really bring us closer?
Yeah, it does. It advances our knowledge of fusion, and it sets a new record for this type of device. So it is bringing us closer, but there's still decades of scientific research and engineering work ahead. So we're a little bit closer now to something that's a really long way away. Experts, they told me this week that we can't take this as a sign that we can sit back and wait for this to come and solve climate change for us. That, there's still uncertainty whether it will work. And if it does, it'll be much too late for that.
So Lawrence Livermore National Laboratory is using ICF, which is this technique where they essentially hit pellets of fuel with lasers. But that's not the only approach to fusion. We also have news about a different kind of fusion experiment today, the JET reactor run by the UK Atomic Energy Authority.
Yeah, so JET is what's called a tokamak reactor, and tokamak reactors contain fusion reactions in a donut shape with powerful electromagnets. And JET's been doing experiments in Oxfordshire since the 80s when it was first set up, and it's been gradually ramping up in power throughout all the time since. It's actually been shut down for good now. It shut down at the end of last year. But just before that, scientists gave it a big send-off. They were presumably less worried about breaking something than they usually were, and they smashed their own record for both the duration and energy output. They also smashed the world record for energy output of any type of fusion reaction.
Nice.
So, yeah, it's a good result. So previously they'd managed 5 seconds at 59 megajoules, but late last year they managed an extra 0.2 seconds and they ramped up the output to 69 megajoules. Which is a nice way to sort of end the experiment. And you can actually hear what the world's most energetic fusion reaction sounds like because they somehow got a camera that could survive the plasma and released a video.
Oh, awesome.
All right. Out with a bang, almost.
Yeah, I don't know what I expected, but that was very cool to listen to.
Yeah, I'm genuinely surprised that they could record that in any way, considering what's going on inside there. So that was JET that you heard, and a new tokamak reactor called ITER is being constructed at the moment that should start experiments in 2025, and that will take things much further and set its own records, hopefully.
As the world gets warmer, our infrastructure keeps running into trouble. That's because structures built a long time ago are facing extreme conditions they weren't designed to handle. And one of the clearest examples of that right now is the Panama Canal, where a historic drought has caused a shipping traffic jam that's having a real impact on the global economy. This week, James Deneen looked into what's happening in Panama and what this means for the future of one of the world's most important shipping routes. Hi, James.
Hey.
All right, so when we talk about old infrastructure, just how old are we talking with this one?
So more than 100 years old in this case. The Panama Canal is, just to refresh, a waterway that cuts across one of the narrowest points of Central America to connect the Pacific and Atlantic Oceans. And since it was completed in 1914, it has served as the fastest way for ships to sail between the two oceans. So it's hugely important for global shipping. Around 5% of all shipping routes pass through it. It's sometimes called a global choke point, because disruptions there have effects everywhere.
And you've reported about how there's a lot of disruption right now because of a drought. I'm sure that low levels on any body of water make shipping harder, but does it get more complicated with a canal?
Yeah, pretty much. So on the Panama Canal, it all has to do with locks, which ships use to pass through the canal. The locks lift the ship up from sea level, enabling it to cross the continental divide on a large reservoir that forms the middle part of the canal, and then bring it down on the other side. Filling those locks takes a massive amount of water, roughly 200 million liters of fresh water for every ship that goes through the canal. And all that water is supplied by a big reservoir in the middle of Panama, and when that reservoir runs low, it causes problems. Now, this isn't entirely new. Droughts have led to restrictions on the canal before, and there's a body called the Panama Canal Authority that governs that kind of decision. But things appear to be worse this time, with the reservoir having fallen to record low levels for several months. That's due both to a surge of ships trying to use the canal, as well as a record drought brought on by El Nino and exacerbated by higher temperatures with climate change. Adding to the problem, nearly half of Panama's population relies on water from that very same reservoir for drinking water, and it's also used for other things like agriculture and mining.
Yikes. I would not want to be the one who's pitting global shipping against the water needs of millions of people. So how is the Panama Canal Authority weighing this balance?
Yeah, it's definitely a dilemma. So the first restrictions came early last summer, but they've tightened since then. Only 22 ships per day were allowed through in December, which is the lowest number since the 1980s, when the whole canal was closed because the U.S. invaded Panama. Currently, 24 ships per day are being allowed through the canal, which is about a third fewer than normal for this time of year. That may not sound like a big deal, but combined with disruptions to shipping elsewhere, it has raised the cost of shipping goods around the world, and it's an even bigger disaster for Panama's economy, which depends on revenue from the canal. Normally, the canal brings in between $3 to $5 billion each year. Now, the Panama Canal Authority is estimating it will lose between $500 and $700 million in 2024 due to this water crisis. These restrictions are likely to ease with the rainy season come May, and El Nino is expected to recede in the next few months. But this is the third time in the past decade drought has severely disrupted the canal, and many people are concerned about more severe droughts with climate change repeating this problem in the future, making the Panama Canal an increasingly less reliable shipping route.
Is the Panama Canal doomed? Like, what can be done to keep it usable?
Well, one researcher I spoke with put it simply, just add water. Of course, that's easier said than done. There are things that the Panama Canal Authority is already doing to use water more efficiently, such as sending 2 ships at once through the same lock when possible. But a spokesperson told me a long-term solution will require far more substantial changes than that. The main idea now is to build at least one additional reservoir to capture more water during the rainy season that can be used to top up the canal when levels get low. But this will be extremely expensive, and the prospect of flooding more land in the tiny biodiverse country of Panama is proving to be a really controversial political issue.
All right, every week we bring you some of the most important science news, but what about wonder, joy, the ineffable, etc.? Escape Pod is one such, escape for you there. This week's episode is all about mass, from a group of insects nearly too light to be weighed to the mysterious and weighty dark matter, and that's already in your feed.
And coming up on Culture Lab next week, culture editor Allison Flood is interviewing the author Naomi Alderman about her latest book, the mindset of disaster prepping, and the mystery of why humans turned to agriculture all those thousands of years ago.
For more than 100 generations, people who are living that settled lifestyle were doing much, much worse than people who are hunter-gatherers. So why did they keep doing it? Why did they carry on with that?
That's coming next Tuesday, right in this feed.
And now we've got some new research on what happens to your brain when you microdose LSD. Microdosing means taking teeny tiny doses of a drug, and at least with LSD, there are some noticeable changes in how complex our brain signals look, even when you don't have psychedelic effects. Grace Wade is here to explain. Hey, Grace.
Hey there.
Let's start with brain complexity as an idea. What does it actually tell us about the brain? What does it mean?
Right. So this is a measure of brain activity that looks at the repetition and novelty in signal patterns as measured by an EEG. The more novel and unrepeated signals, the more complexity. It correlates really well to our level of alertness. People who are asleep, in a coma, or under anesthesia have lower measures of neural complexity, while those who are awake have higher measures. And in this study, the research team wanted to investigate how low doses of LSD compare to moderate or high doses of THC and methamphetamine in terms of changing our brain complexity, as well as whether people's subjective experiences of the drugs made a difference in this complexity measurement. And as you said, they found microdosing LSD significantly increased these complexity measures.
But THC and methamphetamines, maybe not so much?
Exactly, even when those were taken at high doses. And we've definitely seen from previous research that higher doses of LSD also increases neural complexity. But what's interesting about this finding is that participants did not report experiencing the hallucinatory, conscious-altering effects that LSD produces. So a small, subsymptomatic dose was still sufficient to change the brain in this measurable way.
So we can have these complexity changes without the consciousness changes. Okay. But were there any brain changes in the people taking other drugs at higher doses? I can't imagine taking even a quote-unquote moderate dose of THC and not having a different brain.
Oh, absolutely. Just not the complexity measure we were discussing. So those taking THC did report experiencing an altered state of consciousness. They also had increases in the kinds of brain waves associated with relaxation, while people who took methamphetamines had the opposite effect, as you might expect.
Yeah.
What this study tells us is that states of consciousness and neural complexity are really two different things, and you can change one without changing the other.
So is there a therapeutic use for this new understanding? Like, would I want to microdose LSD in order to increase my brain's complexity, even if I knew it wasn't going to alter my consciousness?
Right. So this is something that the researchers didn't investigate, so the study can't necessarily say anything in that direction. But there is an idea this all relates to called the entropic brain hypothesis, which posits that it might be bad to have too little complexity in your brain. In that case, things that increase your neural complexity could potentially be therapeutic. However, this paper can't say anything about that, and we don't have a great grasp on whether there are health risks of microdosing LSD either.
In case you missed it, a volcano in Iceland erupted late last year, beginning in November with a giant rift in the ground 15 kilometers or 10 miles long. And new data suggests the rate at which magma flowed into that crack, it was fast. Really fast. The fastest ever recorded for this kind of event. Michael LePage has more on that story. Michael, when we talk about magma flowing quickly, what are we talking about?
So in this case, we're talking about 7,400 cubic meters per second. So that's roughly 2 Olympic swimming pools full of molten rock every single second. So this magma had been pooling several kilometers below the surface of the Reykjanes Peninsula of Iceland. And then as this crack opened up between the magma and the surface, all of the magma suddenly flowed into this crack. And the speed of the flow it's 100 times faster than what the researchers measured during the recent eruptions in the region. That's in 2021, 22, and 23. And when I say the crack is massive, I should say it's really long and deep, but it's actually just 8 meters across at the widest point. So this crack was the site of what are called fissure eruptions in December and January, and in fact another one's just begun today. So the volcanic eruptions that we are most familiar with are where you've got a single stream of lava erupting up through a central tube, but in this case you've got sort of a line of magma coming up through the crack.
Do we know why it moved so quickly, the magma that entered this crack?
Yeah, so the team think there were 2 factors. So first, of course, Iceland is located on a plate boundary where the plates are moving apart. And so this is generating enormous forces, and it's these forces that led to this huge crack forming. And that crack kind of sucked the magma up as it opened up. But there was also a lot of pressure that had built up deep underground where this magma was accumulating. There was both this push factor and a pull factor. By the way, I should say magma is what molten rock is called before it emerges from underground. So it's lava above ground and magma underground. And magma has been recorded flowing faster in some very large eruptions elsewhere. But for this kind of a situation where you've got magma flowing into a crack, it's the fastest we know about anywhere in the world.
Yeah, and I had a chance to visit Iceland, that same region, a few years ago when one of those other eruptions had just begun, and it's so awe-inspiring to just see rocks that have literally been formed from cooling lava. But I gotta say, what happens to the people who are trying to live there, Michael?
Yeah, well, it's pretty problematic. As one of the researchers told me, it's really hard to predict exactly what the Earth will do. So the team think it's likely that eruptions are going to continue for months or years. And in fact, as I said, another one started today. So these eruptions are happening very close to the most famous tourist attraction in the country, the Blue Lagoon. And the Blue Lagoon is in that place because its water comes from a nearby geothermal plant. And so the Blue Lagoon was evacuated this morning, and now the lava flow has flowed over the pipes that carry the hot water from the geothermal pipe. So that's a serious issue because people in Iceland rely on geothermal power for heating. Almost all the buildings are heated by geothermal power. So some of the towns and regions nearby are going to lose their heating as a result of these pipes being cut off. So it's a serious issue for Iceland, and no one can be sure quite what's going to happen next with these eruptions.
Okay, Sophie, we've got some other exciting news. I need to tell you about the asteroid known as Bennu. So scientists have been hard at work analyzing the samples from this asteroid, and they think that Bennu may in fact have been a chunk from an ocean world based on the data that they've gathered so far.
Wait, how do you learn all that from just a handful of rock chunks and dust?
Right. Well, that's a great question. And there are a lot of instruments involved, including X-ray diffraction, which is this technique for revealing which minerals are in a rock sample. And Bennu seems to have a lot of a mineral group called serpentinites. On Earth, these only form when rock from the mantle is pushed up into the sea and exposed to water. So that's one clue. There's also this rare white mineral that seems to be rich in calcium and magnesium phosphates. And that mineral is also something we've seen in plumes of water from Saturn's moon Enceladus, which is also presumed to be an ocean world under its icy crust. So the thought from these data points is that Bennu could have been knocked off a small ancient ocean world in the early solar system and then eventually made its way to our asteroid belt. Though there are other researchers that say it may be more likely that this ancient world would only have retained water below the surface, so not like pools of water like exposed to space.
So less oceans and more like underground reservoirs.
Yeah.
Awesome. Bennu just keeps getting better. I mean, asteroids, I didn't really know that they could be as interesting as some of the other cosmic objects out there.
I feel like I had the same journey here, but each asteroid may in fact have a story to tell about the origins of our solar system or even other solar systems. And with Bennu, there's this additional excitement that it could also have some clues about origins of life, because ocean environments are thought to be key, and some of the structures found in the Bennu sample may hint at some processes necessary to support life's development.
Well, I also have new news. We've got a new kind of thunderstorm just dropped.
Amazing. I love a good thunderstorm.
Me too. The more dramatic, the better. But these thunderstorms will be a little hard to see because they only happen over the ocean, especially east of South Africa and in the Gulf of Mexico. But what's new about them is the sheer amount of lightning you would see from this one location. Land-based thunderstorms, they've got lightning, but it's spread out. And these ocean storms, they're smaller, but they're also denser. So dense that you could see lightning 8 times per second. So this means the strikes are happening so fast and so close together that the sky must appear continuously lit.
How, though, did they figure out that these storms existed in the first place?
Through satellites. A research team at Los Alamos National Lab was looking at historical satellite data, which has captured and recorded individual lightning flashes. And in one case, in this storm over the Indian Ocean from 1998, they found an instance where the lightning was flashing so close together that the instruments couldn't distinguish individual strikes. It just recorded one long flash that went on for 29 seconds.
Wow. All right, well, one last story. Sophie, I'm going to describe an animal to you, and you are going to tell me what you think it is.
All right, hit me.
All right, it is long and thin, about 20 centimeters or not quite 8 inches long, completely legless, very pink, with scales kind of ringed around its whole body. And it's got a pointy little snout, but no visible eyes. As the riddle goes, who am I?
I was going to say earthworm, but then you mentioned the scales. It doesn't have eyes, so probably doesn't get out into the sun very much. Some kind of cave snake?
This is a really unfair question, Sophie, because the animal in question...
Thanks.
That's all we do here. But the animal in question hasn't actually been seen in 90 years, at least until now. So it's probably not on your radar. But it's what's called a sharp-snouted Somali worm lizard. All those words are its name. Worm because no legs. Lizard because genetically and evolutionarily speaking, it is in fact in the lizard family.
Evolution, you sneaky genius. So how was this worm lizard found if it hasn't been seen in 90 years?
I think that's the most amazing part of this story, Sophie. The lizard lives in a part of Somalia near the Ethiopian border that's been really hard for scientists to access because there's so much conflict in the area. But a charity that's working on clearing landmines there, which means digging in the ground, found one in the course of doing their work. And they sent a photo to a researcher who confirmed it was this very specific animal that hasn't been seen in almost 100 years. And what that kind of says is that there might be a lot of biodiversity that the research world is missing out on because of wars or conflict.
That's it for this week. Thank you so much for listening. You can find all the stories we talked about today in the show notes. And you can subscribe to this podcast on whichever app you're using to listen.
Plus, if you like the great stories we're bringing you, please give us a rating or review on Spotify and Apple Podcasts. Keep that algorithm happy for us, please, and thank you. We'll be back next week. Bye for now.
Bye.
This podcast is produced by OG Podcasts. Find out more at ogpodcasts.co.uk.